Okay. We are recording. So what I'll do is from today onwards, so till date, we have studied a class of algorithms called model-based, which is just basically a class of reinforcement learning algorithms, which are model-based. As in, what is model-based? That is the model of the environment is known. And what do I mean by the model of the environment being known? Let us try to understand by seeing an example. Okay, so recall that we had a policy pi which mapped from states to probability distributions over actions, and we had a transition probability p of s given. So next state given the previous state and action, right? So let me draw the diagram once. So let this be your state. You take an action A and you go to another state S dash, and you get a reward for this transition, right? This is all your entire RL framework. So what did we discuss? We said that we want to maximize the long-term reward. So we devised the value function. So for a particular state, S, we said the value function according to a policy pi is given by, anyone can recall? Or if you want to make it even simpler, the Q value function given a state and action. You don't remember what is this? So this is the summation over
gamma power I R from S to S dash.
Okay, so
A.
st plus I, at plus I, and st plus 1. This is what you're saying, right?
Yes.
Plus I, of course. So I from 0 to infinity. This is the long-term reward. So every reward you're going to take, you will just sum them up. All the rewards you'll get in the future till infinite. So this is, in this case, it's an infinite horizon setting. Doesn't really matter. Even if it is not, at the end, the value function will become 0. So all of them have the same similar Bellman equation. So it doesn't matter. So now what did we do? We simplified this. And each time we are doing the same thing. How did we simplify this? We said that gamma to the power I st plus I, or st, at, and st plus 1. Okay. So plus what did we do? Summation of, we took gamma. Basically this summation, the 0 I am writing separately and 1 to n I will write separately. So I equal to 1 to infinity gamma to the power I. So more than, you can put 0 also, no problem. I'm just putting gamma outside. So gamma to the power I r of st plus I plus 1, at plus I, so st plus I plus 1, and st plus I plus 2, given st equal to s and at equal to a. Right? This is what we did time and again. Right? And then what did we do for this term? Do you remember?
We condition again and use
Okay.
Q pi. Yeah.
Yeah, we'll use q pi or v pi, whatever we want. I'm going to use v pi. This will become, so this is I is 0. So expected value of overall policies, the reward RST TST plus 1. Even we can just write S A S dash plus gamma times V phi of S dash. Given ST is equal to S, AT equal to A. Correct? This is what we wrote. This is the value function. Now, what do we know between the value function and the Q value function? So what is V of S? How can we write this as? This is nothing but the expected value, yes or no, overall actions? Yes or no? Do you agree?
Yes.
So for a
Yes.
particular state, you have a list of actions. You will just take the average of all the actions. So that's what we are going to write. We wrote this as, so summation of pi for all actions in state. And then we wrote the reward function. And then we wrote the expected value of pi. S prime plus gamma times V pi of S dash plus given ST is equal to S and AT equal to A. So this is what the Bellman equation we derived. So but now there was a big assumption, not an assumption, but we said that when we write this expectation down, we could write it down, right? We said we could write it down. How did we write this down? And now if the environment's model is known, what is known? Probability of S dash given S comma A and the reward, the 3-argument reward function, which we also defined as the expected one-step reward. If these two are known to us, then what can we write this equation as? We can simply write using Lotus, yes or no? Conditional expectation. We can write this as summation over all states in dash the rewards of SAS dash plus gamma times V pi of S dash into probability of S dash given SA. Yes or no?
Yes.
So, but now look, so this is what I wanted to show here. So we have seen this time and again here, but what I want to tell you is most cases in real life, most cases in real life applications, comma, P, the transition probability matrix, the transition matrix P of S dash given S comma A and reward function R is unknown, right? So this is unknown. So if this is unknown, this is question mark. Similarly, this is also question mark. So this is called, when that happens, we need model free RL algorithms. So from now onwards, we'll discuss model free algorithms. We have discussed all the basics about model based algorithms. We'll now discuss model free algorithms. This is the model based algorithm. Okay. So now what does this model free RL algorithm mean? So that's what would be our topic of discussion. So just letting, so for example, I'll give you a small example. So let's take an example. I think some of you told me that you have already used it before. Example. Okay. Say you have right? What you have something like you want to compute expected value of a function of a random variable. Okay, correct. So x say is sampled from a distribution x. Okay, so what? How do you write this using Lotus? This is some integral over f of x px dx. Yes or no? This is the distribution, the PDF. Fine. This is Lotus. Do you agree? So just take the expected value. So now, if I don't have, if px of x is not known, instead yi is equal to f of xi, where xi is sampled from p of x is known. Can you tell me how will I compute this expectation? I have taught this in class. The sample expectation. So I told you by law of large numbers. I proved the weak law of large numbers. For example, the weak law of large numbers. What does the average value, expected value converge to? 1 by n. We did this in the first few classes, no? Yes or no? Just the empirical average. Correct? Just take the average of the function. Whatever value, that is yi is f of xi. Whatever sample you have in the data. Fine? Okay, maybe this is too simple for you all. If you have no questions, so let's go. So now do you agree? Here as well, we have two expectations, yes or no? We have expectations over p. So this entire function can be, do you agree, written as, what can this be written as? V of s, v pi of s. Two expectations. In terms of two expectations, how can I write this? So the inner expectation is already written. This expectation. One expectation where the action is selected based on the state. And the second expectation where the next state is selected based on the state and action. Yes or no? And we can write this expectation as st equal to s and at equal to a. And we have the reward function sa s dash plus gamma v of v pi of s dash. Yes or no? Or just the summation over all this is equivalent to the summation over all the rewards. All rewards. Do you agree? Fine.
Yes.
So now what can I do? So if I have lots of expectation, what can I, if I don't have this distribution, what can I do? Instead of the distribution, what do I have in real life? Instead of distribution, our agent will have data only, right? For example, you go on a cycling, you train an agent to cycle or balance a unique one wheel. It will know the current orientation and everything, and it will know when it will falling, but it is not going to know the implicit distribution of the states, right? Of the transition matrices. Will it know that? It will not. So it will know something like this. S0, the action you took at S0, the reward you received, then whatever state you went to, the action you received, the reward you received, S2, and so on. Yes or no? This is what you will get. In real life, you have data. Fine. So this data can be used, right? I can use this data somehow by the same concept of large numbers. So what is the function over here? The function is this, yes or no? Whose average you want to find, correct? So we want to find the empirical average now, empirical average of this. So again, recall in our first few days, we used to call this the expected value of GT. The expected value. So this thing, let us call this as GT. GT given ST equal to S, whatever you have. Fine. This is all you want to find. So now my question to you is, this is what you want to find. What will you do? Again, GT is this just the summation of gamma I reward of ST plus I, AT plus I, ST plus I plus 1. I equal to 1 to infinity or 0 to infinity. For one, this entire thing is called one trajectory. Say, for example, this ended in some Sn. So this is the terminal state or whatever. So this gives you one trajectory, right? So this, for example, is Sn page ends. So you say this is one trajectory. So from this trajectory, I will get one value of GT, yes or no? I can just add these rewards. Yes or no? Do you agree?
Yes.
Very good. So I can get, so say this trajectory. So your data today, all the class, I will be writing this as, say you have trajectory from 1 to n. So whatever trajectories you have. That's what I have written over here, but I don't, where is this? Yeah. So say you have this trajectories and you have a list of this trajectories. So not only once, say you play one chess game and you have all the state action reward, that is one trajectory of until the end of the game. And you play thousands of such games, right? So that will give you thousands of data points like this, some trajectories like this. I'll give you a graphical example, but the intuition is clear, right?
We have total m trajectories.
Correct. Say we have m experiments.
Okay.
Okay, fine. Good. So now what do I say? So for here in this case, I wrote n, but let us just put m. I'll tell you whatever trajectory I'm going to use. And so these I will put the trajectory ID on the superscript. Okay, for throughout the session, I'll be using this. Whatever trajectory, this is second state of ith trajectory. So you have say m trajectories, and now I want to use them to find out the value function. Say, okay, very nice, very easy. How do I do it? So again, recall by law of large numbers. Large numbers. So for trajectory I, say it began at state S. So do you agree this will be GT of I? Fine with everyone?
Yes.
So now what I'll do is I will say that V pi of S will be approximately equal to summation of, or just GT of, say, the indicator variable, the trajectory I, sum over all I from 1 to m. And you need to put an indicator. You have to tell me what indicator it will be. And then summation of I equal to 1 to m, the same indicator. Basically, this will counts number of trajectories starting at I or S here in this case. Fine. So just count the number of trajectories starting at S. Okay. So what will I do? Tell me, what should it be? Simple, no? Just for example, ST of I is going to be, for now, let's forget about T. So let's say G of I. You start with S0. Then S0 is, which state do you want S0 to be? You're finding the reward you receive when you are in state S, right? You start from S. So this should be S0 is equal to A. Good. That's what I'm saying. So the first state is S. So this is all you have to do. So you could have simply written 1 by m summation of gi, but that is not going to work. Sorry. Because all this time, the extra trajectories may not start from the same state, right? And we'll see how to go about doing that. It's fine with everyone? Clear?
Yes.
So this conditioning means that this condition has to be brought in, that the first step has to be starting from S. That's how you're imposing the condition. So this is the data structure also, as I was saying, this is say tau I is the trajectory. And now let us take a concrete example to see what would be the, how would we compute the Monte Carlo samples. So, okay. So Monte Carlo is nothing but just using law of large numbers. The most important law in all of statistics and all machine learning, any data science, because we never have access to probability distributions. We only have access to data. So every time we have to bring in expectations and we have to use sample expectation or empirical averages to approximate some expectations, right? So this is just using the law of large numbers and computing empirical averages. That's all it is. So it's a fascinating name maybe, but there's not much to it. So Monte Carlo methods, I'll just show you some trajectory here. So for example, you see there are two trajectories, tau 1 and tau 2 covered over here. So tau 1 and tau 2. So I'll just, tau 1 is in red and tau 2 is in blue. Okay, so there are two trajectories that are given to me. And I want to compute what have you. So there are few things to observe. So when you look at this graph of states and time, what do you observe? What is given to you? Can you tell me? So what are the states in this system, in this environment? First, tell me the states.
1, 2, 3, and 4.
Good. So there are, so this is again, we are sticking to tabular methods. So this also will change as we go ahead. In tabular methods, states are known. States are in a table. In real life, that also can change because the environment will be just determined by some features and there can be continuous variables. You cannot uncountable number of them. So states can be uncountably infinite. So still considering countable case, we'll slowly get to the last phase. When we get to the last phase, we'll deal with those problems where we don't have access to anything. We neither have access to the model, neither we have access to the state space. But here we have access to the state space. So, okay. So the states are 0, 1, 2, 3, and 4. 0 is the terminal state, as we have defined in the previous class in stochastic shortest path problems. Stochastic shortest path problems. Stochastic shortest path. Where at any step your problem may terminate. For example, a chess game. You can keep on playing a chess game. It can end in any stochastic number of moves, but it will end nonetheless. It cannot go on forever. Fine. Okay, so let us see. So we have two trajectories given to us. We have 4 states. And in a question, we have been asked to determine the value function for state 2 and 3. So value functions of state 2 and 3. So let us do state 2. 3 you can do as your homework. You can try this as your homework so that you know how to do it. It's a very mechanical procedure, but anyways, let's try and do it. Okay, so for state 2, so we'll be using only for the first time, we'll be using the first visit method. What does the first visit method mean? So now do you observe that v pi of s is given as the expected value of gt given st is equal to s. Can you tell me what does it uh, assume? One thing it assumes in common, and that's the reason we'll be taking a few, what do you say, a few assumptions, and we'll do a few things that will be trying to solve this thing. So what is it taking is it does not depend on, this is for all t, right? Yes or no? Correct. It doesn't depend on which t. So this left hand side does not depend on t, right? Does it depend on t? But the right hand side says that. So basically we are saying the policy at 1 is same as policy at 2 and so on at policy n. And we define this as a single policy, stationary policy that does not change, right? Just like the Markov chains, we did the stationary distribution, just like that. It does not change over time in an invariant distribution, right? Correct. So we can take at any time point. So any time point. So basically what I'm trying to convey to you is, so say V2, so V cap. So I'll denote this as an estimate. Cap is an estimate. And I will give a numerator for this. So trajectory 1. So this is from trajectory 1. Trajectory 1. So can you tell me the time points that are important? Which time points? And this is for state 2. Can you tell me the time points which are important here? For trajectory 1. So, okay, if you are, I'll just write it in red so that it's the same color. Or let's do it for trajectory 2 first, then I'll try to do it for trajectory 1. V pi of 2, state 2. Tell me the time points which are important. Anyone? So we are dealing with the second state, right? Second state. And we are trying to find out the value function from the second trajectory. So from the second trajectory, if I want to find out the value function, so tell me when does the trajectory go to state 2 at what time?
0.
Good. So you can clearly see, I'll put a box around it. At time, so at time t equal to 0, the trajectory is at state 2. So I will use everything from 2 onwards, like state z at time 0 onwards. Yes or no? That's what I said to you. That's what the equation is. Yes or no? GT is the summation of all the rewards, all the subsequent rewards.
Yes.
So what will it be? So it will be, just let me write it down. So gamma, so this is R1 of 2. No, I'll write the same ink, sorry. R second trajectory, first reward, plus gamma times second trajectory, second reward. So I'm just putting down the values which have been written on the path, right? Plus gamma squared times R3 and all the way to gamma to the power. So gamma to the power of n minus 1. Say, so Li is the trajectory length, L2 is the trajectory length. So RL2. Fine with everybody? So L2 is the trajectory length, same. Length of tau 2. Fine? No
Yes.
doubts? Okay. So now, if that is the case, what can I do next? So this is the, do you agree this is only one of the values I'm going to get? Is there any other place where it goes to trajectory true? So it will not go to trajectory true at all, ever. Correct? Fine. So I'm in this case, it is just the first visit method. So I will select only the first visit to a state in one trajectory. So this is just a heuristic. You could select all the visits or you could select just one visit. Just depends on number of samples you're getting, right? So similarly, if I try to do the same for from trajectory 2, so trajectory 1, so can anyone tell me what are the points important? So from trajectory 1, if I want to find out the value function of state 2, what are the time points important?
1 and 2.
So I have 1 and 2. These are the two time points. So now I'll tell you, I have told only the first. I will only take the first time it visits that state. So I'm
So
going to
only
take
one.
good. So I will just take trajectory 1 and I will write it down as R21 plus R3 gamma R3 sorry, R31 gamma square R31 dot gamma to the power of, sorry, this is 4. Gamma to the power of L1 minus 2 gamma to the power of, or R to the R of L1 minus L1, right? This is all I'll get. I'll put sum up all the rewards. Do you agree? Okay, so I get one number, one estimate from each trajectory. I will get more trajectories. I will get, say there are k trajectories for state 2. So now what can I write the v pi of 2 to be? Can you tell me? Approximately 1 by k summation of
The empirical
vk.
mean.
Very good. K equal to, or I'll just put I here, maybe I equal to 1 to k. That's it. So that's basically it. There's nothing more to it. So you just take the value function for every trajectory and you add them up. So it's much simpler than trying to do. So all we were doing is we take the value function for every trajectory, every trajectory and add. Fine. Good. So now next thing I'll be doing today is I'll be doing what is called as, so we have discussed V1 of 2, V2 of 2, and V3, and this are your homework. Please try and do the state 3 and we'll try and see it next time. Okay. So now we'll do at every visit. Okay. So the every visit method is, so now remember, recall. Again, the time points are not important as we assume a stationary distribution of transitions and policies and rewards. Right? We assume that these rewards and all the model that we have of the environment does not change over time. So in this case, we can account for every. So in this case, we can account for every sub trajectory. So in early visit method, you can account for every sub trajectory that begins at a state S. Do you agree? Fine with everyone?
Yes.
Since we do not change the policies, we can do that. So now again, I'll just copy this diagram once down. It's easier to. Okay. Now I say that I'm going to consider every trajectory. And I will use this notation V1 for the trajectory ID. Again, use the same colors for simplicity. V2, I will use which are we using for state 2 are we using? We're just going to find for the red trace state. Okay. So I will be using for the trajectory 1, V1 and second state. No, now Noedit told me that at state in trajectory 1, we visit state 2 at t equal to 1 and t equal to 2. At 2 time points, we visit the state 2. Now, if that is true, what I can do is I can just write, say t equal to 1 at t equal to 1, I will write one trajectory, one value function, right? I'll get one value function for it. So let us try to write it down. What will it be? It will be R2, the same value function we had written, plus gamma times R3 plus gamma squared times R4 all the way to gamma to the power L1 minus 2 times R L1. So now this is at time equal to 1. Now I say that I'm not just going to restrict myself at time equal to 1, not just restrict ourselves to t equal to 1. Instead, what will we do?
We
Instead,
will
we'll do
find that
this.
t equals to 2 as well.
Correct. Instead, I will say that because it is time invariant, I will use every possible data I am getting, every possible partition. At 2 as well, I'll find. And I'll get R3, 1 plus gamma times R4, 1 all the way to RL1 gamma to the power L1 minus 3. Right? Similarly, from state 2, similarly, from trajectory 2, I will have V2 t at 0 of 2 to be what? Tell me. It's going to be the same,
R1
right?
plus, yeah, same one.
So it will be just the early visit value as it only visits 2 at t equal to 0. So now once I have all these value functions, I will do the same thing. I will say that my value function at pi, say there be da 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 da. So I will say I will number these as trajectory t. Say I have 1, 2, and all the way till k. So I will name these. So I'll say this is named as V V3 of 2. And this is named as V2 of 2. This is V1 because it's a countable set. I can keep doing that. So now again, I'm just putting the notation in the subscript to make you for easy to understand. And then Vi of 2, and I'll just sum over all the k's I equal to 1 to k. And this will be a V pi of 2. Any doubts? Any questions? So this is where we sort of understand what we have to do to compute the value functions. Okay. Similarly, you can try as your homework. Use early visit method to find q pi of s comma n. Okay, you will be able to do it. The same procedure. All you need to do is also make a, so all you will need to do is, again, it's a tabular case setting. A1, A2, dot, 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 AK, and state 1, state 2, and state n. So for every state, you will get an action and you will see that for every, you will try to get data points for in every state, what people have taken an action there and try to get the eventual reward they received, right? You'll be able to write it down this way. Please give it a try. We'll do similar things in Q learning, but for the timing, you can also do the Monte Carlo based stuff. So now, once we've understood this, I'll slowly get into one of the most popular algorithms in reinforcement learning, that is called the temporal difference algorithm. Often told, often cited as the learning process of our brain. Process in our brain. So what is temporal difference is what we'll try to understand now. So now we'll use the same Monte Carlo idea, but we'll try to condense this notation for the time being. We'll say we use the every visit method. We're going to use the every visit method. That is all right. This is one thing. And I will say that say use we will say for a state S0, that is what I've written on the left hand side. The rest of the if the rest of the trajectory is S0, S1, dot, 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 Sn, where this is the terminal state, I will define the reward of the mth strategy. Say this is the mth strategy. Not strategy, trajectory, mth strategy, trajectory. I will define that as S0M. We'll put a bar as well. And I'll say that, so what is the reward you got from S0 to S1? What is the reward you got from S1 to S2? And dot, 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 what did you the reward you got from Sn minus 1 to Sn? This is all the list of things we'll be writing down. So I'll just take a sum over S0, S1 in the mth trajectory, S1, S2 in the same trajectory, all the way to Sn minus 1, Sn in the mth trajectory. Okay, so we define this reward as the total reward from a state S0 in the mth trajectory. Okay, similarly, if I asked you what would be r dash of S1 in the mth trajectory, what will it be? You can put your gammas as well, no problem. gamma 1, and this is not really going to affect a lot of things. Okay, so just can you tell me? Any idea?
First will be R S1 and S2 under
Correct.
trajectory M, and then plus gamma times
Good.
so on.
So every time, so now we have a list of numbers, right? We have condensed our approach of GT, whatever we were writing ST given S. We have samples from them in form of R bar S from the mth trajectory. Correct? Yes or no? Do you agree? This is what we have. This is the GT. This is a one sample of GT. Correct? The sum of all the rewards from M. No problem. So since it's a finite horizon problem, I will just not, I'll put gamma equal to 1, and that's not going to be a problem at all. So I'll just put gammas, I'll throw gammas out for the time being. It's a SSPP problem, stochastic shortest path problem. So gammas are not required. Fine. So all I'm going to say to you is, I have an estimate of GT, whatever expectation I was going to get, I have that over here. Fine. So now for a particular state S, do you agree I can write this as 1 by n, whatever, am I using n over here? I'm using m, so okay. 1 by m, k equal to 1 to m, reward of for that state and for that trajectory. Yes or no? Fine. Only consider if S was visited in the kth trajectory. Otherwise, we don't need to consider it at all. Okay. So can you tell me, so is this fine with everyone, my law of large numbers? This is approximately estimating what? The GT given ST is equal to S. Fine.
Yes.
Okay. So now what I'll try to do is, so I have written down the definition of the R bar or whatever it is, and I have also written down the value function that I can write. Sum over all the rewards of all the trajectories I've written down. Now I will try to bring in the temporal difference term. We are told to prove for the mth update, this looks something like this. So how do I prove it is the question. So okay, so now say I have, say that, so this is question 1 for the first derivation. Say we are dealing with the mth trajectory in an online fashion. What is an online fashion? That is, you get, so that you have your computer, you get the first trajectory, second trajectory, third trajectory, and all the way to mth trajectory in a sequential manner. And you have to keep updating your VS, right? Sequentially update. Do you recall where did we do this? Anyone who recalls? We did it somewhere. Bandits. So okay, fine again. So we say that Vm plus 1 is it? Yeah, Vm plus 1 is the trajectory, is the output that I want to compute. Will be 1 by m plus 1, k equal to 1 to m plus 1, reward of that state and for that trajectory. So now tell me, if I know that, can I do some manipulations with it? to only account for the m plus 1th number? Any idea? Okay. So what will I do is I will write this as two summations. 1 by m plus 1, k equal to 1 to m, reward of is k, and 1 by m plus 1 of reward of is k, that is m plus 1 is trajectory. Is this fine with everybody? Fine. There's a small typo on the left hand side. You can just put 1 plus 1. Okay. What I do is I take the m plus last reward and the rest of the reward. Last reward and the rest of the rewards. Okay. So if I do that, can you tell me what can I write this as?
We can make it m by m plus 1 and then make a Vm of s.
Good. So if I multiply and divide by m, I get this as Vm of s. So I get r bar of s m plus 1, 1 by m plus 1 plus m by m plus 1 Vm of s. Good. So now to simplify stuff, I'll just what I'll do, I'll add 1 and subtract 1, and I'll get Vm of s. So from this first part, I'll get 1 plus 1 by m plus 1, the reward m plus 1 minus Vm of s. Correct? Fine.
Yes.
So that's what we are told to prove. And then this can be an update. This can be your Vm plus 1 of s. M plus 1 of s. Fine. So it is also in your homework. So this is say 1 plus 1. So there are a few properties it must hold. The summation of m should be infinity, and the summation of squared of m should be less than infinity. We have discussed this in the Robin-Munro algorithm. We do not want the error. Second term is the error. So we don't want the error to go to be accumulated till the infinity. But the first term is all the evidences. So we want them to stay. So it was done in the Bandit's ODE explanation. Same thing. And it's also in your assignment trying to prove log 2, log n plus 2 by 2 n plus 2. So that is fine. So all these are learning rates, step sizes. Fine. That was just a detour. No, that's not important. So what's important now is, so given the step sizes and everything to us, now I have got this term, right? So now what I want to do is I want to rewrite this update rule in this form. Sum of differences. And what does this sum of differences mean is what are we going to consider currently. Okay, so let's try to do that. Okay, so what I'll try to do is I will use this equation. So Vm plus 1 of s is equal to Vm plus gamma of m plus 1s r s m plus 1 minus Vm of S. Okay, I'll use this equation. Fine. And I will try to find out some equation that will be helpful. So let us say I am interested for the kth state. S is any S. So I'll just put a subscript for easy computation. We'll see why it will be easier. But I'll just put a subscript. So indicating the kth state. It's fine. And this M is the value at mth time at learning. If you're not following, please stop me. Okay. So now what I'll try to do is I will write down this. I'll expand this. So let me expand this. So if you remember this R bar of skm plus 1, what is it? Can you tell me? In terms of the rewards. So this is the sum of all the rewards. Rewards in trajectory. Which trajectory? S0, S or SK plus 1, SK plus 2, and so on. Yes or no? Fine. Okay. So this we can write this as SK to SK plus 1. I'm not putting the trajectory, trajectory number for simplicity. So at the end, I can write SK plus 1, SK plus 2, and all the way to SK plus whatever, SN, SN minus 1 to SN. Yes or no? I can write this. Right?
Yes.
This is the sum of all rewards. So now I have a term SK that I have over here. And I want to do some manipulations with it. So I have minus V of SK. Right? So I will say that I subtract V of SK and I will do one addition. I will add VM SK plus 1. Okay. Similarly, since I have added it, I will also have to subtract it. So I will subtract VM of SK plus 1. Okay, this is a legal step, correct or not? Do you agree?
Yes.
So now again, similarly, if you have understood this, I will write SK plus 2 and I will put VM of SK plus 2, VM of SK plus 3, and so on till the last VM of Sn minus VM of Sn minus 1. So everything gets cancelled, right? Everything is fine, except which terms? When you have a difference of summations, your class 11 maths, all these terms will just get cancelled, right? Only the last term and the first term will remain, correct? Fine.
Yes.
So now, and this term will be 0 because we have said terminal state, no reward. So I can safely put that as well. Fine, no problem. This is already known to us at the terminal state, there is no reward. So now I can write VM plus 1 of that state SK as this VM SK plus gamma M plus 1 of SK, and we have a list of the summations I equal to 1 to or K2 I equal to K2N minus 1 reward of SK or SI Si plus 1 plus V of Si plus 1 minus V of Si. Yes or no? This is all what I'll have. So once I
Yes.
write this in this form, good. So once I write this in this form, look at this on close observation. That is the reward of Si plus 1, reward of Si plus 1 plus V of Si plus 1 minus V of Si. Look at it closely. Do you see something over here? I will term this currently, say for this is again at the mth step or whatever m plus 1th step. And this is m, this is m, this is m, the mth update. So I will say that this is the mth update for the state I. So what does this mean? From I'm going to I plus 1. I'm getting a reward R of Si plus 1. Fine. So, and I say that, what do I say? Just look at it very carefully. I say that I have an estimate. I have an estimate of Vm of Si. Yes or no? That is the estimate for the expected reward from state I. But now I say that no. Why one step reward? Why current 0 step reward? I don't want that. What I want in turn is I will take a decision, a reward. I will see what reward I get. And then this term that I have over here, I will also have an estimate from VSI plus 1, right? And when I have an estimate for VMSI plus 1, but I have got a sample from the reward. So I know a better estimate. So for example, I am in a current state. I am in the university as a UG student. I know that on average, on average, my future is going to be like this. I'm going to be a software developer, or I'm going to be going into higher academia or something. But now I say that I take an action. I write I do something, I do some research, and I get the action, maybe a research proposal, and I get a reward of a paper. And then I know the value function of that as well. So when I have that paper, the state I will be in, I would be more likely to be into getting into colleges in higher education. So what I'll try to do is, when I'm not taking that step, what is the estimate of the current reward or the current state versus when I'm taking the step and I'm observing the reward and I know the value function of the next state. I deploy this task to the next state and subtract. So this is the one step estimate. And you subtract the 0 step estimate from it. And you say that this is the difference in expectation for the current action or the current whatever decision you take. That's the decision. That's why it's called the temporal difference. It's called the temporal difference. So it's called the temporal difference. And then what you will do is you will basically write this entire thing down as Vm plus 1 of S, K, whatever you want to write as Vm of Sk plus gamma m plus 1 of Sk. And you will have a list of difference terms. I plus 1m and dot what? In minus 1m. Fine, this is what I'll have. So now you can see one more big advantage of this. Can you tell me the advantage? There's a big advantage over here. Any idea of the advantage? See, these are all linear terms, right? Linear terms. This all this dim plus 1 and so on. So if they are linear terms, the advantage is I can write this online. I can take, so every step can be used to update the value function of the state. So basically you can write this as gamma s is equal to v of s is equal to this plus gamma of s d. So if you are in state s, what is it going to be? So the differences every time. So this is one update. And next time you get one more update, you can just keep on adding them. And as m tends to infinity, v tends to v pi. The same proof that we did last time. Is it clear? So I've written this down over here for a particular state. If you go to the next state, you observe the reward and you just put in the value because you have this entire temporal difference term that I proved just now. And these are all summations. So it's basically every step. So it's if you write down the algorithm, say in step S, say you are in state S, take an action, go to S plus 1 or sk and sk plus 1 or s, go in state S, go to S dash, whatever you want. Observe the reward. The reward S of S dash. If you observe this reward, so I can update the state value as basically this gamma times r of s s dash plus v of vm of s dash minus vm s. So every time you take a step, you keep on updating the value function of that state. You keep doing it every time you go to a particular state. And that is shown to converge to v pi. Fine with everyone? Any questions? I'll wait for a moment before I go to the last algorithm of today. Any questions? Can you hear me?
Yes.
Okay. So now I'll be teaching what is called the TD lambda algorithm. Lambda algorithm. So this is often called the TD0 algorithm. TD0. Let us see what is the TD lambda algorithm now. Why? And then we'll see why it is a TD0. Now, say for a lambda between 0 and 1, let's get this clear out of our way. 1 minus lambda times lambda to the power I, summation of 1 to infinity is 1. Yes or no? Or 0 to infinity is 1. Correct? Right? Any doubts? Right, so you can just take this out and this summation is 1 by 1 minus lambda. Great. So what do I mean by why am I doing this? My claim is lambda to the power I and Ri, if I have a summation like this converges. Converges if say Ri is bounded by some constant C. So if it is infinity, then you don't know. It's bounded by a constant c, which is less than infinity. So then I can write this as an upper bound as 1 minus lambda, lambda to the power I, c. So this just becomes c. So it shows that this summation is finite. That is why we are going to select a lambda between 0 and 1, and we'll be using this weight for something. So this is the convergence of infinite weighted sum. Okay, now I use that. That is fine. Good. So now what I try to do is, let us try to recall the value function equation. So what is the value function equation? Anyone? So for the time being, you can forget the actions as well. Say you are in state S, st is equal to s. So how can we write this? We can write this as summation of r of st plus i plus 1 I equal to 0 to infinity. Correct or wrong? Right? So again, we can write this as rs0 or st plus 1 plus summation of I equal to 1 to infinity, or you can put 0 to infinity as well, st plus I plus 1, st plus I plus 2, given st is equal to s. So again, the same trick I'm going to use. I will condition this on st plus I plus 1 as sum s prime and so on. So say I will get the reward s to s dash plus v of s dash. St is equal to s. Okay, so this is your one step Bellman equation. This is just 0 step. Now, if I have this one step Bellman equation, can you tell me, can I write a 2-step Bellman equation as well? Can I use this further to write by induction another equation like this? Rs dash s double dash plus v pi of s double dash. Do you agree?
Yes.
Fine with all of good. So now this is the 2-step Bellman equation. And anyone, can you tell me why am I calling this 1 step, 2 step, and so on? What is the intuition? So 2 step would be st plus 1 plus st plus 1, st plus 2 plus v pi of st plus 2. Correct? This is clear. Why is it called the 2-step? Why will it call the 2-step Bellman equation? So you see, again, it comes from this fact of st. In one step, you go to st plus 1. Yes or no? And you have an
Yes.
estimate of st plus 1 here. So you can have this estimate either by just using v pi of st, or you can see the reward that you are taking from st to st plus 1, st to st plus 1, and see the estimate of st plus 1. Correct? Yes or no? It's both the same thing by definition of recursion. Right?
Yes.
Now I can also do another thing. I can not take one step, I can take 2 steps. And data allows me to do all this very easily. Doing it over expectations, you will have to write cumbersome joint distribution, but data will give you all the expectations out simply. S plus 2, V of ST plus 2. So again, this entire thing is again the same as V by. Yes or no? Do you agree? So I'm just breaking up a difficult problem into smaller problems. So if I write this down and I say I write L minus 1 or a L step Bellman equation, what will it be? Expected value of summation of I equal to 0 to L minus 1 or just L, is it? No, L minus 1 because this is one step. Where is one step? Two step, this is one step. So one step is at S. Okay. The reward at st plus I, st plus I plus 1 and b pi of st plus, tell me the last term. Yes or no? So see the two-step Bellman equation. This is L most likely, no? Yeah,
Yes.
st plus L. Fine. So this is your STL plus, I'll just write 1 st plus 1. St plus 1. Okay. So now this is st plus N. So now I tell you, okay, I have written this down all right. And this is L plus 1 step. So this is fine as well. This is L plus 1 step, and then you can do the same thing all over again. So let me, for the same notation, I'll just use the L plus 1 step itself. So this is L plus 1 step Bellman equation. I will just write st plus L plus 1. Okay. I'm just adding 1 to the entire equation. Finally. So L plus 1 step Bellman equation, I wrote it down. I take from the current step, I take L plus 1 steps and I figure out the entire rewards and I keep adding. So now I tell you all of these are correct estimates of V pi, yes or no? Do you agree? Yes or no?
Yes.
So now I tell you that if they are all correct estimates of L pi, so what I'll do is I will use all of them. Why to just use one? These are all correct estimates. All correct estimates. I will use all of them. What will this help me? It will help me. Why? It will help me because I will get more samples. Yes or no? More samples means more law of large numbers pay, you'll converge better. Yes or no?
Yes.
So that's the idea. So first term is lambda. Then I'll just put 1 minus lambda, 1 minus lambda, lambda. Next term will be 1 minus lambda, lambda square. This is where I'm bringing in the weighting factor. 1 minus lambda, lambda to the power of L. Fine. Great. So now I will simplify this equation. And what can if I add all of these, what will I get? I will get 1 minus lambda, the expected value of L equal to 0 to infinity, lambda to the power L, summation of I equal to 1 to L, reward of st plus I, st plus I plus 1 plus v pi of st plus L plus 1. Do you agree this is fine with all of you? This is because I just wrote down the nth term. So this is the nth term and summed over over all L. Fine, no doubts. Okay, if there are no doubts, can you tell me how can I simplify this? So I'll first simplify it into two terms. I'll break it down into two terms. And then, so where is the, so I'll break it down into two terms. I'll break it down into the first term will be 1 minus lambda times summation of L equal to 0 into infinity lambda to the power L summation of, I'll write down the same first term, R of S T plus I S T plus I plus 1. This is one expectation. And the other expectation will be, tell me, L equal to 0 to infinity lambda to the power L my plus 1 V pi of ST plus L plus 1. Do you agree?
Yes.
I just wrote down the first term over here and the second term over here. So let us try and simplify term 1 and then we'll try and simplify term 2. So this is what I've written down. I have proved this and we'll try to prove this term now. Okay. So the term 1, I'll write as the summation of, just copy it. It's easier that way. This is there. Now I'll try to minimize, simplify this term. So now look at this term carefully. So if I look at this term carefully, for L equal to 0, what do I get? L equal to 0. For L equal to 0, what do I get is the question. For L equal to 0, I get just what? One reward, right? The summation, inner summation becomes R of ST and ST plus 1. Yes or no?
Yes.
For L equal to 0, the summation is over I equal to 0 to 0. So just the 0 term. Then L equal to 1, I get RST, ST plus 1, RST. One ST plus 2 plus R of ST plus 2, ST plus 3. Right. So I'll write this way. That is also written. So now, how are we presently summing? We are summing presently horizontally, right? This is how we are summing in this above summation. Yes or no? And then we are summing whatever we sum them to be. And then we sum the rows together. That's how we are summing this, right? The L is summed later. I is summed first. Correct? So all the columns are summed first, then the rows are summed. Do you agree?
Yes.
So I do the reverse, where I sum all the columns first. So on, and then I sum all the rows. That is, I sum up all the rows and then I get a summation like this, and then I sum them up. That is also the same thing. So what can I write these two summations as? So first I'm summing over all the i's. So I equal to 0 to infinity. Do you agree? Okay. And then for I equal to 0, what else are there? For I equal to 0, what are the values of L it takes? Just look at the rows. I equal to 0, L is equal to
0.
0, 0, 1, 2, all the way to infinity. Isn't it? Entire
Yes.
I equal to 1, L is equal to 1, 2, all the way to infinity. Fine. I equal to 2, L is equal to 2, 3, and so on. Do you agree? So I will write this as L is equal to I to infinity, correct? Just see, there is a diagonal term. No, here it will become I to infinity. Isn't it? Everything below the diagonal means it's from I to infinity. So I will write lambda to the power L R of st plus is the same. It will be the same thing, st and st plus I and st plus I plus 1. So now once I do this, do you see an advantage? I write this summation in this way. Do you see an advantage of simplification over here? Can you?
We can use the summation of lambda L here. It will cancel with 1 minus lambda.
Yes, this term is independent of
L.
L. Good. So I will just sum over I equal to 0 to infinity, reward of st plus I plus 1. And I will have 1 minus pi summation of lambda to the power L equal to I to infinity. So clearly I can take lambda to the power I common here. If I take lambda to the power I common, this summation becomes 0 to infinity. Yes or no? Fine.
Yes.
So if I'll just put the lambda to the power I over here. So I will write I equal to 0 to infinity lambda to the power I R of st plus I plus 1 plus 1 minus lambda summation of L equal to 0 to infinity lambda to the power L. It's not plus, sorry, into. So this term goes to 1. So this becomes this is our term 1, which clearly just weighs the losses by this lambda term. What does this do? Just weighs the reward by lambda to the power I. Fine. As you go into the future, you discount out the rewards. That's how we have done it in the future, in the past, right? Am I saying done in the future? Sorry. That's how we did it in the past, where we just discounted out the rewards. So this is term 1, no problem. Term 2 was what? term 2 was expected value over pi, summation of I equal to 0 to infinity lambda to the power I plus minus lambda to the power I plus 1 v pi of st plus I plus 1. Is this the term? Yes. Now, can you help me solve this? This also we can do some trick clearly. So let us write down a few terms. It will help you understand that better. So lambda 1 minus lambda v pi of st plus 1 is the first term. 1 minus, so I'll expand this and write maybe minus lambda v pi of st plus 1, lambda v pi of st plus 1 minus or st plus 2 minus lambda square v pi of st plus 2 and so on. Do you agree? V pi of lambda to the power st plus I plus 1 minus lambda to the power I plus 1 v pi of st plus I plus 1. Now, can you tell me, can you group things differently over here? There's a way to group things differently that you'll get a single summation. Any idea? Just have a look at the equation. See, there's a lambda term over here. No, I can group these two. Do you agree? I can group these two. I can group these two. Yes or no? Now all the terms diagonally.
Yes.
Good. So I can keep grouping stuff like this unless you reach the the last state, whatever is the last step, which is the terminal state. So we can do that. So what I'll get over here is I'll get lambda to the power I v pi of st plus. Tell me what will it be? This be
I plus 1
I plus 1 minus v
minus
pi. That's it. Do you agree?
yes.
And I'll have a remaining one term left. V pi of sk plus 1. Right? And I can subtract v pi of sk and add v pi of sk. So this is how the algorithm does it. V pi of sk, it adds to the equation. So we say that since we're anyways estimating v pi of sk, so it's not necessary to put it in the expectation because we'll be at the end of the day removing the expectation by sample v. But the basic idea is add and subtract v pi of sk and you get expected value of summation of I equal to 0 to infinity lambda to the power I v pi of st plus 1 I plus 1 minus v pi of st plus I and v pi of k, not k, no, t, sorry, pardon me, st. Okay. So this is what I got. Once I get this, now I can add both the equations. What will I get if once I add both the equations? Term 1 and term 2. See term 1. Term 1 is just the reward to the power lambda I, right? So clearly you see you get the temporal difference terms once again. So 1 plus 2 gives you v pi of s t as defined as v pi of st plus. So this is defined as. So this is the next sample, m plus 1. You can write this as Vm. So this is the new updated value of st. This is term 1, term 2 plus term 1. So you get expected value of summation I equal to 0 to infinity lambda to the power I r of st plus I to st plus I plus 1, st plus I, st plus I plus 1 plus v pi of st or vm of st plus I plus 1 minus vm of st plus I. Fine. I just added 1 and 2 and I got the same temporal difference terms, right? So basically, what did I get? I got an update rule Vm plus 1 of Sk or whatever St as Vm of St plus expected value of summation of lambda to the power I, the temporal difference term d, I from any trajectory you want, I equal to 0 to infinity. Do you agree? This is what you're going to get? Fine or fine, not fine. So now I will tell you why this is important. Once we derive this update rule, it becomes important to understand. Let's try to visualize this. So we derive two temporal difference equations, right? But I told you that you may be thinking when I told from the first to the second, I'll just show you two algorithms. So now look at this algorithm. So this algorithm we derived basically from the scratch, just taking all the possible steps. Well, all Bellman equations. Fine. So now if I put lambda equal to 0, what will I get? Can anyone tell me? So again, it's a temporal difference term. So I will just replace the expected value by a learning rate gamma. The expected values are again sample averages. Now tell me, if I get this equation, so again, which equation am I talking about? Lambda to the power n, this equation. Once I get this equation going, because I have an expectation, I'm just updating the values one after the other. I'm doing a stochastic descent or whatever stochastic ascent here. This is the learning rate. So when I'm doing this, when lambda is equal to 0, what is going to happen? Just tell me. You will get Vm plus 1 st is equal to Vm of st plus gamma m d of 0m, yes or no? Lambda to the power lambda equal to 0 to the power 0 is equal to 1. Rest are all 0. Correct? Any doubts? Only the first temporal difference. So this is exactly why I called the first algorithm to be the TD0 algorithm. Look at the algorithm that when I was deriving this algorithm, I told that I can update whatever I could because I had a summation of over all of these. I could keep updating, but none of you asked me, Dada, why are we just not considering the subsequent delta or the D's? Why are these not being considered when I'm updating? If I convert this to this is not the exact thing. You did not ask me that. So that's the reason when we are doing it one step and only one update online, that's the temporal difference of 0, the lambda value of 0. That is one step Bellman equation you are taking. But if I put lambda equal to 1, lambda equal to 1. Do you agree I take the entire trajectory? This is one step. St plus summation of I equal to 1 to infinity di of m. Do you agree with this or not? I take the entire trajectory. All temporal differences. This is TD of 1. So TD1 is the one that I derived first in this case. Clearly, this is the TD1 algorithm. And this is the TD0. And we generalize the TD0 and TD1. We have by using a flexible tuning parameter lambda that we can tune between 0 and 1. If you select it closer to this, you select single step properties, single step TDs, and this is full trajectory temporal differences. Questions? I'm happy to go over stuff once again. We have some time. Any questions? Am I audible?
Yes, দাদা ওই 0 to the power 0 equals to 1 ওই পার্টটা একবার যদি বলে দাও।
But that the idea is 0 to the power 0 is just like anything to the power a to the power 0 is 1, right? So we don't, any
No.
power is 0.
না মানে 0
That-
by 0 তো ওটা
Yeah, that is
technically।
true. So technically that is true. We just define this term. So if
ওইটা
you put limit,
ডেফিনেশনটা এইভাবে।
yeah, it's basically what you can do is like take limit lambda tends to 0. That's it. You cannot put equal to 0, but since it is clearly lambda tends to 0, when I'm putting lambda tends equal to 0, the property you are getting, that is the same property you should, for continuity, I'll define it at 0 as well.
Okay.
So this is, so initially, so I expected, so what the entire thing completes when you try to, you get to understand that from my, what do you say, from my Bellman equation, I got this equation where I had the entire temporal differences. But suddenly I told you, no, you don't need the temporal differences of everything. Just take the current step and update. And that's the shock for everybody. So I didn't reveal the shock at that time because I didn't want you to think about it. So I told you just take the current state update, st plus 1, and you just update. This is what our brain does basically. A lot of neuroscience papers have shown that what your brain does is currently takes one step, sees the reward, and computes the temporal difference of the rewards and updates your actions accordingly. So what actually is happening here is you are doing it one step at a time. But now in the real life, you have the entire trajectory given to you. And this is a very big dilemma that you are in. So do you want the entire trajectory, which makes it extremely slow? Or do you want a small sequence of S, which makes it very fast, but very noisy estimate? So that is being accounted by using this lambda. So when you use this lambda, as you make it closer to 0, you count less and less steps into the future, making it faster. And as you go towards 1, you make it more converge. What happens is you make it less noisy, but it becomes slower. And because you take the entire trajectory of the TDs. Okay. So there are no more further questions. We can stop here today. We'll discuss off policy and on policy algorithms next time. Stop recording.